and one of the co-organizers of this school, and it's a pleasure for me to introduce this talk of Professor Michelle Johnson. I'm very glad to this possibility. Michelle is currently Associate Professor of Physical Medicine and Rehabilitation at the University of Pennsylvania. She has a secondary appointment as an Associate Professor in Bioengineering and is a member of the Mechanical Engineering and Applied Mechanics Graduate Group. She has a Bachelor of Science in Mechanical Engineering and Applied Mechanics from the University of Pennsylvania, and a PhD in Mechanical Engineering with an emphasis in Mechatronics, Robotics, and Design from Stanford University. She completed an NSF NATO postdoctoral fellowship at the Advanced Robotics Technology and System Laboratory at the Scuola Superiore Sant'Anna in Italy. And currently she directs the Rehabilitation Robotic Research and Design Laboratory located at the Pennsylvania Institute for Rehabilitation Medicine at the University of Pennsylvania in the School of Medicine. The lab is also affiliated with the General Robotics Automation Sensing Perception. Dr. Johnson's lab is specializing in the design, development, and therapeutic use of novel, affordable, intelligent robotic assistance for rehabilitation in high and low resource environments, with an emphasis on using robotics and sensors to quantify upper limb motor function in adults and children with brain injury or at risk for brain injury. Dr. Johnson has spent over 20 years applying technology solutions to aid in the understanding of disability and impairment after brain injury. Today we'll continue the theme about application of robotics and we'll give us a talk on socially robots for neurorehabilitation in high and low resource settings. So I don't want to waste other time, and I will leave the stage to Michelle. So please, Michelle.
I just had to change locations, I apologize.
Michelle, can you hear us? Okay, perfect. We see you, but we don't hear you.
Hello?
We hear you.
Can you hear me? Okay, hold on. Give me a second, one second. I apologize. I realized that where I was a little bit too dark, so you couldn't see me. And so I wanted to make sure that I was in an optimal environment. Okay, so thank you Fabrizio for that introduction. I'm going to cover kind of a little bit about rationale for neuro rehab in general, and I'm assuming that some of the talks prior covered a little bit more about neuro rehab, especially Dr. Mazzoleni's talk, and I'm going to go into more defining what social robots and social assistive robots are, and then talk a little bit about some inspiration that I feel like as roboticists we should be looking to human-human interaction to try to understand a bit about how we should build these robots. And then just talk a little bit about case studies, both what I've been doing and other people. It's going to be more high-level type discussion. So clearly we're motivated by the fact that we're having a lot of people surviving injury, disability, surviving diseases, and specifically neurorehabilitation is about people surviving injury to the nervous system. And we're talking primarily, for example, injury to the brain would be resulting from maybe causing a stroke, which would result in paralysis. Injury, infectious diseases also cause both the neural, central, and peripheral damage, For example, many of you know that COVID-19 is beginning to be seen as a disease that have been leaving both cardiovascular, but as well as cerebral damage, cognitive and physical. And then also thinking about this in terms of both adults and children, and that there are diseases that occur in the perinatal stage, in the infant stage, that result in neurological disorders like cerebral palsy, autism, and Down syndrome. So there's a growing number of these folks across the world. And across the world, also in the United States, we're facing a shortage of clinicians and people to care. And I think this shortage was very clear when we thought about, COVID, and we saw what was happening, and we saw the numbers of people who were, as the infection rates came and people were being admitted to the hospital, that we just didn't have the capacity to support the people that needed care. And I think this problem is just, COVID just showed it in like a very quick way, but this problem has been happening, and this gap in care, I think, is worse in some countries than others. In low and developing countries, you can see it more. And clearly, because we're engineers, or and I'm an engineer, I definitely, and I think from the talks that you've seen, we believe that technology can help bridge this gap. It's not the only solution, but it's one of the possible solutions. In this case, we're talking assistive robots. We'll classify social robots under the whole assistive robots paradigm. And there are lots of different types of assistive robots. Dr. Zola just talked to you about prosthetics and these types of assistive robots. We're wheelchair type robots. The ones that I'm going to focus on are kind of what we'll call socially assistive and service type robots that are interacting with people with neurological impairment for the purpose of therapy, assessment, observation, motivation, demonstration, and things like that. So one of the earlier definitions of what is a social assistive robot is a type of robot that aids human through social interaction. And this might be pet type robots, some of the earlier robots like Paro. If we get to it, I'll talk a little bit about Paro, because I'm not sure who on the call would already be familiar with those types of companion robots. And then service robots that are functioning, to serve people with neurological disabilities, but also elderly as companion, and a variety of different service. And service could also be therapy services as well. I want to step back and just talk a little bit about the reason for why I put high and low resource settings on my talk, because I'm very passionate about the fact that rehab robotics should be a global affair, and not just in high income countries, but also in low resource settings and developing countries. And so I wanted to, from a paper that was published in collaboration with Dr. Zolo's team, we looked at kind of where robots were across the world, and thinking about the fact that they're mainly in high income settings. We think that where you see these yellow dots are kind of where majority of the innovation is happening in robotics. However, and there's some things happening in what we would call upper middle income countries and some developing countries. I put the red where I know of particular colleagues working in lower income countries, and wanting to call attention to the fact that majority of the diseases and neurological injuries that are occurring, they're actually happening outside of high income countries. And so there is that gap that's happening. A lot of the technological solutions are happening within spaces that in themselves, urban versus rural, might be dealing with issues of disparities. So I'm not saying that the disparities is not within high income countries, but also just thinking globally that a lot of the stroke survivors, 80% of strokes occur outside of high income countries. And so there is a need to really think beyond maybe our own countries and think about solutions. And I think the key at guidelines is being affordable and multi-purpose is something to think about when we want to move beyond. And affordability, I want to bring up the World Health Organization, talk a little bit about cost-effective thresholds. And one of the things is thinking about the gross development product per capita for a country and kind of saying, well, what is cost effective? I think the reason for having this workshop on soft robotics, because I do think that soft robotics gives us this opportunity to even explore how we can make robots more effective using the soft robotic the inventions and the soft robotic tools. And I think that's why we were really eager and happy to kind of have this particular workshop, because we wanted to call attention to that. I just want to define that so that when you're thinking about it, what does the World Health Organization consider effective? And if we look at the gross domestic product, for example, let's look at the USA. I mean, I'm in the USA right now. It says the average income per capita of the average person in the United States is $53,000. Of course, we know that that might be quote unquote the average, but there are lots of people who make a lot more than that and a lot of people who make a lot less than that. But for the sake of doing the average, but compared to a country like Botswana, that GDP per capita is 7,000, around 7,000. We see that a robot that would be built for 150,000 or 30,000 US dollars may not necessarily be the best robot to apply in Botswana, which is in sub-Saharan Africa. It may not be cost effective to be there. And if you do put it there, it may only be very difficult for hospital systems, if they're not private, to try to even recoup their funding stream. So thinking about as a rule of thumb, as we design these systems, to try to think through interventions and developments that are highly effective. And if push comes to shove, 3 times the GDP per capita is what's considered cost effective, and just trying to use that as a kind of a general guidelines for thinking through the development. I think social robots give us an opportunity to do so. A lot of problems with current systems, they're mechanically complex. They are huge or larger than we want them necessarily to be, and they're also high cost. And so a lot of things that we've been working with in a part of kind of discovery here is to think about potential strategies to reduce the cost, to be more multi-purpose by, using lower cost systems, lower degree of freedom systems, 3D printing, soft robotics, and units that can be reconfigured. Mattia, do you have a question, or am I just seeing your hand go up? Wasn't sure.
Sorry, it goes up.
Okay, sorry. All right. So this concept of like, how do we think about introducing more lower cost systems within neurorehabilitation and within therapy. And so, we see people making a variety of efforts here in terms of trying these different strategies to reduce costs. We don't see that as much in the soft robotic, in the social robot space, but there are efforts to try to think about how do we bring social robots to this affordable level, including my lab and other labs there. So social robots for neurorehabilitation, I asked this question, what should they do? And I think that a lot of our efforts have been, as engineers, have been not as collaborative as we should be, and studying kind of what is happening within the hospital spaces so that we can understand how best to build these systems. So I undertook with a colleague from Temple to try to say, can we study human-human interaction to understand and inform human-robot interaction? And the interaction that we wanted to study was kind of therapy, patient and a therapist within a stroke population. So basically the ideal neurorehab space, stroke survivor with brain injury, have paralysis in the upper extremity. My colleague was an occupational therapist, and we wanted to say, well, what are the key features that we need to understand in this human-human interaction and to study it in order to design better robots in general, therapy robots, social assistive robots, etc. So typically when we want to engineer the interaction between the human and the robot, it requires, and we do this already pretty well, understanding the therapist's movement and backing that into kinematics and modeling the movement, understanding the force interactions and backing that out into the haptic equations and the models that we need to develop these connection with these robots. And something we don't do as much is also understanding the behavior and the roles that's happening during those interactions, so that we can think about, from a social robot perspective, what are the physical cues, what are the verbal cues, what are the cues that are actually occurring within these interaction dynamics that help us understand the intent of the therapist during these behaviors. So we kind of knew that there are lots of work out there looking at kinematics and haptics, but not enough looking at the intention and the behavior and the roles therapists take on. So we decided to look at a set of videos, and these videos were actually videos used to train therapists, and they're with stroke survivors, and it's human-human contact, human-human demonstration, human-human support of relearning a particular task. So this is just an example of the video up top with a very low functioning stroke survivor and how the therapist was supporting this person, trying to get them to relearn this particular behavior. Another video here, for example, is this sweeping video where you see the therapist trying to teach, he's more high functional than the lady that you saw before, trying to show and teach him how to do this particular practical task and what to do and how to do it. So so in terms of taking a look at these activities, and what did we want to do? We decided then that we wanted to model behavior in a simple way, similar to how we kind of think about a stimulus and a response, right? And that if we want to think about interactions in terms of something triggered the therapist to respond, but with a particular behavior, and that something triggered the therapist to interact with the patient in some specific way. If we try to use this stimulus response model to try to characterize intent, and working with our occupational therapists, they actually came up with physical and verbal cues based on their knowledge space that they believe are very typical within the human therapist interaction setting. Therapists would often do reaching, gripping, moving, lifting, transporting, stabilizing, guiding, etc. And the patient is usually trying to execute a particular task. And what are the cues that the therapists use to try to decide that they need to help? If the patient's not reaching, if they're not gripping, if they're not coordinating, if they're not doing particular movements, then the therapist is going to intervene. Verbally, what are the things that the therapists are doing? They're explaining the action. They're giving motivational type speeches. They're trying to understand where, in fact, is the patient having trouble, or trying to explain that and give them cues and directions. They're also like commanding, do this, do that, and they're also explaining, stating, well, we're doing this because, and also correcting verbally. And stopping. So what's the patient looking for support? They're usually asking questions. They're usually possibly complaining, sharing about pain, sharing about awkwardness, things like that. So once these were coded, we decided then, how do we envision that, had a hypothesis that this is how these things interact, that the therapist and the patient were for example, acting together, co-actors in a dyad, and the therapist move from demonstrator, the patient is observer, the therapist is, something happens, maybe they're finished demonstrating the activity, and then now the therapist is the observer, the patient is the performer, and then something happens, maybe one of those cues, the patient is not reaching well, the patient's not moving fast enough as the therapist might be expecting, and that then triggers a transition in the role where the therapist is helping and the patient's performing. We had our occupational therapist do a qualitative look at these videos and coded them in terms of what we talked about. And this is an example of what the coding might look like from a stream, is that here's the therapist as the actor, the patient as the client, and we hypothesize that there would be a demonstrating behavior observer and helper, and while the client is doing the correlated behavior. And so if the therapist is now demonstrating an activity, something happens that then switches their role, and at the same time, what is going on with the client. So we're kind of looking at the co-actors in this space. A couple of quick results, finding that that all three roles were taking on, that the demonstrator and observer role was a lot less used than we anticipated, and that most 50% of the time the therapist was helper and assisting, and about 40% of the time they were observing. Something to take away. Well, we realized that these relationship and frequency might have also been due to the level of function of the patient that you're working with. So, example, if the patient is higher functioning, you might end up with higher levels of observer and performer than you would assistants. If the patients are lower functioning, then, and like the videos that we had, you would end up with higher need for the social robot to be more as an assistant and as a helper. I think the reason why we didn't see as many demonstrator observer where the therapist was demonstrating a particular task was because maybe where did the video get cut? But what we do when we observed real time within a actual hospital environment, or outpatient setting, we actually did see that there were more time spent in the demonstrator role, but definitely that time was a lot less than the observer, performer, and the helper roles. So that's something to keep in mind as you think about applying social assistive robots to neurorehabilitation. Maybe the question is, what role are you applying, and what do you want them to do, and what type of patients that you're working with? One of the other things to think about here is what cues did we often see within this small subset of tasks. We saw a lot of the cues that often triggered the therapist was the patient not reaching and the patient not lifting. And also, and this made sense because we were doing a lot of activities of daily living. So, and also there were not gripping that would trigger the therapist to intervene. What are the things that we saw the therapist kind of doing? We saw the therapist supporting, lifting the patient, providing a lot of light touch kind of interaction in terms of the physical human robot interaction. We'd expect maybe that the robot would apply some light touch, but we saw a lot of the therapist supporting the hand, supporting the forearm, coming in and stabilizing the person's arm as they do. We saw a lot of patient asking questions, describing, wanting to understand something, and then we saw a lot of therapists explaining, encouraging, asking the patient to do specific things. So in terms of learning from the human-human interaction, it also made me say, well, what are we already doing in our field in terms of supporting patients? And what we see is that the helper role, actually, we've developed a lot of robots with helper role. There's the therapy, the traditional therapy robots that we see that are permanently connected to the person's arm, to the person's leg, and helping them do movement could be considered very much robots in the helper role. I think the demonstrator and observer roles, we could see those as our service robots, as our socially assistive robots, like this picture here. And I think what we don't often see is the physical connection and the transitioning between contact and non-contact. And I think a part of that is due to what Dr. Zola was talking about, the safety issue, and how do we regulate if we're going to move into touch and move out to not touch. How do we regulate that? And I think that's why we haven't seen as much robots transitioning clearly. But I think as her talk actually illustrated, that the idea of using compliant systems and soft materials might actually overcome some of these issues. This is an example what I was talking about, the helper role. And here is an example of a demonstrator observer role. I'll talk more about this particular system because this is one of my PhD students doing this particular idea of using a social robot, developing an affordable robot to demonstrate a movement with a patient, and using camera and vision systems to try to collect information about the movement and define and provide metrics and information to the therapist. I'll go through that a little bit more. This is also an example of physical human interaction, in that here now the robot is not just the robot is demonstrating and asking the patient to interact with them and expecting some type of physical interface. And so it's not just a hands-off type, which is usually typical of social robots, but there is what we call now a physical human interaction that is also happening. And I'll also talk a little bit more about this system. And then how do we move from supporting, observing to helping? This was kind of an idea. We built a hand that had like a soft silicone space to try to decrease the impact of a light touch. And this was a master's student of mine just experimenting with how do we teach this robot to recognize when something that does not reach, and then to move into to reach. This is an example of that. So I would kind of want to deep dive by doing a little bit of case study on the different types of systems that are out there. And actually, while I'm doing this, I would love for you guys to kind of like imagine how can soft robots kind of come and be a part of this process? What's the best way to utilize the things that you've learned to apply, and to be able to do some of these interactions, and whether it actually applies or not. So a big area is the social robots is coaching. And the concept of coaching is trying to figure out, well, first thing, what are you coaching? So, and where are you doing the coaching? Are you coaching elders? Are you coaching young infants? Are you doing it in the school? Is the purpose rehab? And let's assume that most of our purpose is neurorehab and helping people to move again. A very lots of work has been done and thought about in terms of the use of, for example, the Na and this Bandit robot. And oftentimes it's about kind of programming behavior-based control. The speech is important, what actions the robot does. And in this case, it's kind of capitalizing on demonstrator observer robots and being able to see transition between demonstrator and observer. We see that a lot. What we don't see a lot is the transition between demonstrator and helper. I think more and more groups are trying to do that. This is kind of a look at the Bandit robot. This robot was developed at USC, University of Southern California, Dr. Matarek's lab. And the idea behind Bandit was essentially to create a a humanoid type system with a mobile base. This was kind of a first pass. It also a system that they taught like specific physical therapy type exercises, and the system then demonstrated the exercise to the user, and the user then was asked to repeat. And the question is this something that is useful for exercise therapy for stroke survivors, for frail elders, etc. A lot of these social interactions are evaluated with surveys and some classic systems where you're asking about, was it usable? Is this system, did you establish a companion? Did you think the system was intelligent enough? Would you use this as an exercise companion? And as you see from some of the outcomes here, that people actually felt that that this system was enjoyable. Notice they also, in this particular experiment, they looked at the physical system versus the virtual system, and versus a combined system. And you saw that the physical system may have been perceived as more useful, more enjoyable than just seeing the robot image projected at you. So that could suggest that, again, people want to kind of have the robot being embodied, and that appears to be a nicer or something that people find more useful, especially the stroke survivor or the patient. This is just them moving from the Bandit system. And then this is from Yale. The idea here is now the robot is not just demonstrating an activity, but is functioning mainly as an observer, where the robot is looking and watching the patient complete the task, and here figuring out when to verbally intervene to provide encouragement or exercise or some guidance, verbal guidance. This is a quick example of social robots with kids here, and this idea of what the robot being an observer and being able to provide feedback to the child as they're interacting. One thing to think about is there have been groups, and I should have probably grabbed an example of this, is the huggable robots, like social robots that are soft and have fur, and probably the most famous one is the Paro system. But those robots are not usually functioning as coaching, but more as like companion systems. So this is another soft quote robot. This, in terms of using this within the context of training kids and in terms of exercise. As you can see, typically there are behaviors that you program with the robot, and the idea of trying to elicit and motivate kids to do the exercise that they don't want to do. So I'm going to deep dive a little bit more into kind of what we thought about when we were saying, okay, if we want to move from just a social robot to a robot that has physical and human interaction, kind of what are some of the things that we did. From a high level, this work was conducted with a colleague from Oregon. She was actually a PhD student at the time, and I was co-advising through Dr. Kuchenbecker. And the idea was to think about neurorehab, frail stroke survivors and frail elders, and how could this humanoid robot, Baxter, some of you probably already familiar with it, how could it work side by side with the therapist, with the patient. The concept is that the robot would function as a therapy assistant. It would be programmed by the therapist to execute a variety of games and exercise that the patient would then interact. Why did we choose the Baxter? For safety reasons. It was originally designed as a manufacturing robot, but to work side by side with people, and we found that because of its limited power and force profile, that it could indeed work well with older people, younger people, as well as frail, the population that we were going for. The idea was to build games. 8 games were built, and the mimic game was that the robot did an activity and then wanted the patient to play it. The patient taught Baxter an activity, and then Baxter had to mimic you and to play it back. So some games were totally non-contact, like this Robogaga game where it was like robot yoga. And then this flamenco game where the robot was showing the person dance moves. 2 games that required a lot of energy. For example, we're in Philadelphia, so boxing and Sylvester Stallone is a big icon. So the idea of creating a strength game where the person was basically having to wake the robot up, beat, box with Baxter, lots of interaction using the robot's accelerometers to understand the level of interaction and energy that the person put into the game. So the concept then here was, with physical and versus non-physical interaction, whether there was a preference, whether people felt like they could work with the robot. Here's an example of a flow chart of one of the games. In this case, this was the robot. It played a note, moved. Notice that the face is being changed here. Key thing, Baxter was actually not really it was observing but not using cameras. It was observing using sensors, the accelerometer sensor, the information to tell whether the person interacted with it or not, but it wasn't observing the actual motion and movement of the patient. How do we assess it? I mean, I think the key thing in social robots and when you're designing these things is to think about how you're going to assess their usefulness. One possible way is this NASA TLX. It's a task load index. It's very popular for assessing robots. It's talk about task demand, cognitive demand, physical demand, temporal demand, and giving this to patients to get an understanding of how they interacted, whether they felt it was a chore. A lot of in this area, a lot of like survey tools are used often, but there's a cry for more tangible sensor-based tools to really also assess movement and pattern. Another popular one is thinking about emotion. For example, this is very simple. It looks at emotion, engagement, power, and the patient basically says, oh, this best describes how I was feeling. This best describes how whether I enjoyed it or whether excited interaction. This is just 2 example of surveys that are often used. A process for looking at these robots is to think about, pre and post interaction is very important to assess. For example, when the patient came in, they just saw the robot. They just had an impression, and they were asked, do you think this using this robot is a good idea? Were you afraid to make a mistake with the robot? Some key things that we wanted to know. Did you like the presence of the robot? Could you do activities? So these are things that kind of like we're getting at, is this robot, do you trust it? Kind of understanding people's initial reaction. And then after playing the games, we survey them again. So probably a couple of things to point out is that people always maybe are more cautious when they first see the robot than after, which is good, because then also to see the trust level increased after they encountered the robot. And also this idea of the robot as a social engagement, we didn't see as many significant changes there. And the level of comfort also increased. We did a study where we looked at young versus old interacting with the study, and we saw that pretty much there wasn't any major difference between how young people and old people, and older people interacted with the robot, which actually is pretty good because it suggests that the games or the activity was transgenerational, I should say. Another one that I want to call our attention to is the use of these systems for kind of telehealth, telemedicine. And I think this is particularly even more something that we should think about even more in these infectious disease. COVID caused a lot of focus on telemedicine and assessment. So this is one of the work that you had seen the video before, talking with my PhD student who kind of were looking at the use of an affordable a social assistive robot that could be placed in low resource settings, in rural settings, and could be used as a telepresence tool, so the clinician can dial in and then use the humanoid robot to try to encourage movement. Just acknowledging folks. So the concept was, could we make it so that it's are initially less than 10,000, and what should we prioritize? That's our first. So we did like 2 iterations of this. First, we just tried the concept out with off-the-shelf system, the Now and the Vigo robot, to say this system probably together was about $10,000. Would this be even usable? And then we ran focus groups and demonstration studies to say, in a inpatient rehab setting, and in a what we call a nursing kind of home type facility, a skilled nursing facility, but that was like an all-inclusive care place where elders would come during the daytime. It's not a hospital. They come, there are clinicians there, they play, they do a variety of activities. So we asked healthcare professionals in that interaction space versus healthcare professionals in the inpatient rehab space, what they thought about whether this type of system would be usable or not. And we asked them, a variety of questions about the robot, how would they change it? What would they design? I think this is important. Again, my motto is, before we go and develop the system, and I think is to understand kind of the complexity of the neurorehabilitation settings that we want to deploy these systems in. So quick outcomes were in the inpatient setting, and is more like a hospital setting versus the daycare setting, that senior daycare setting, that there was essentially more openness to the system in the senior daycare setting than in the hospital setting. This was done way before COVID occurred. And I'm curious as to whether, if I ran this study again, whether things would change given how people have increased their openness to telehealth and telerehab, especially in the era of COVID. We also asked about, what are your priorities? What are the things you want? Portability, ease of setup, cost, low cost, affordable, maintainable, and durable. One of the key things is, I think, as you get away from the hospital setting, cost becomes more of an issue, and so we need to consider that. These were things that they wanted. They wanted in both settings. The healthcare group wanted different things from the robot. And you see in the senior daycare center, it was a lot of like encouraging them to do exercise, doing reminders. And then in the inpatient, outpatient setting, it was more exercise and therapy and cognitive exercises and things like that. So then I wanted my student to then take what we rediscovered and redesign the system. Can it be more accessible, more affordable? And so he started with the things that the therapist wanted to do, and then one of the challenges is, should we make the face more animated? There was some concern that the Now robot was kind of static. So he started with thinking about how to create or how to interpret faces. He then successfully designed a mobile base, a humanoid robot that can be removed from the base, and then a telepresence platform using real sensors and and cameras. We're now able to collect visually the data and applying machine learning techniques to try to understand what's going on. So these are just some quick slides. You've seen this video. And one of the key things in terms of the analysis here is looking at, is the humanoid robot needed, and does the humanoid robot help improve the execution of exercises? And so this is just the flow of like getting the video information and processing it into clinical measures that could be usable by the clinician. And i.e., one of the biggest complaint of clinicians right now with telehealth is that they can't touch the patient, or they don't have a good sense of what's happening, and visually it's not always clear how to measure, fine, okay, well, is that normal? Is it not normal in terms of movement? Some of that can be gotten, but in a tele rehab setting, and in a tele setting where the clinician is not co-located, you lose some of that fidelity. So we actually did a major survey where we looked at perceived usefulness. We showed therapists the video and we say, would you use this? And again, we want to kind of understand some of the things that they think they could have done with this. I think the key thing we saw was that they really saw that they would use it for communication, that they felt that it was useful. They recognized that it was a good motivating tool. There was a mixed review on whether it could really do the assessments that they wanted, and they also thought that it would improve compliance. There was really inconclusive in terms of whether it would support adherence to exercise. And that's a little counter to some of the work that people have done that suggests that robots would improve exercise. Here is kind of like a full picture of the clinician and the patient is the interaction, and we want to improve this type of interaction even when you go remote. So how can then the robot support what the clinician needs, diagnostic information, emotional information, receive the commands, and then provide motivation, instruction, and perception information to the patient. So my student's running a study right now, kind of looking at in-person versus social robot versus a telepresence type action to understand, what preferences and whether the physical robot was needed or not. I'm gonna just talk a little bit about another effort that we were doing in an elder center, where we were, again, it's the same senior daycare center that we used in that previous study. And this was a collaboration between nursing and it was NSF funding and an industrial partner. And we were looking to capitalize on the idea of how do we develop a low-cost mobile assist for people with a variety of neuro conditions in this senior daycare center. Good methods, focus group, trying to understand what the stakeholders needed, and then deploying the system in kind of different iterations and getting feedback. And we wanted to do what we call a participatory design process. And I think this is important for socially assistive robots, is because, and even for any robotic system, I think is a participatory design strategy is always good to get like current feedback. And I think you've seen evidence of that throughout our presentations. So just a quick, this was published in terms of, first we went in and asked questions. And we wanted to know, what would people want a low-cost assistive mobile robot to do? One thing to draw your attention to is when we looked at the clinicians, the caregivers, and the elders, the elders had different priority than the clinicians and the caregivers. In terms of accomplishing tasks, the elders were more excited about robots actually doing things for them. And the clinicians were less excited about that. When you look at health and safety, the clinicians were more excited and wanting health and safety issues, while the elders were like, I could care less. I think that's something to note, that when you're putting this system within these environments, they're competing desires for what this system should look like. What was surprising was that everyone wanted the robot to support personal connectedness and meaningful activities. And that's actually something to think about. So that's actually an advantage of these particular systems. And then when we think about cognition and supporting, dementia, that wasn't a priority for the elders, but definitely was priority for the caregivers, because they found that in the day-to-day supporting of the elder, their cognitive ability actually determined and increased their load in terms of supporting the elders. This was a list of we ranked some of the key things that the elders were asking for, and trying to come up with a solution that optimized everyone's desire. We ended up thinking about hydration, social connection, manipulation, and monitoring. Our first deployment with this system was a simple social robot that didn't look like a humanoid. Deployed it to bring water, to talk and interact with the patient and ask them about how they were doing. We learned some things about the design there, and also understood how to improve on that. So that ended up for a second deployment. This time we went with a Wizard of Oz approach, where we drove the robot around just trying to get an impression of how people would interact with the robot. And here we were focusing on a walking task. This video is so this is an example of the robot walking an elder and watching, taking the elder for a walk. How did the elder respond? And we collect the data, like what did they say? Did they interact with the robot? Did they even appreciate it or not? The other deployment was the manipulation, looking at putting a novel manipulator on the robot and thinking about the robot playing games. So in this case, we contrasted the robot's functioning to support the game versus a human clinician functioning versus a collaborative type activity. So this is just some videos. Something to take home is that the elder actually in many ways preferred the human to the robot, which actually I think is reasonable, but they didn't mind the robot in certain activities. And they also, where they actually had issue was when the robot messed up. And then they perceived that there were some difficulty in terms of the gripper function, because we were actually playing around with a couple of different grippers. And so the gripper function actually made a difference in how the robot was perceived by the patients. For the sake of time, I'm going to move a little bit. I know I started a little bit late, but I want to make sure I cover everything. Our next interaction is thinking about whether the elders, in terms of thinking about social interaction, prefer a humanoid robot to a robot that still does all the function but may not be as humanoid looking. And in terms of right now, we're settled on, with our collaborator, developing this Quarry robot here. It doesn't do manipulation, but we are looking at whether this system could do the walking task, could, given a skirt or a basket, could help direct in terms of the water task as well. When COVID hit, all our ideas went out the water, and so we actually pivoted and looked at whether the Quarry could be supporting access and screening in the daycare center, and whether it could be seen as a robot-based assessment of safety when it came to COVID. So that's kind of where we're going next. The other quick thing to talk about is robot as companions. I mentioned that could be a really nice use of soft robotics and social robots. I'm just going to mention a couple as a case study, this Paro robot and this Jibo robot. Jibo was a concept that came out of MIT, which is this idea of a social robot within your home environment. And I think where I think this is useful, it is not a soft robot, but what it does embody was this idea of an active animated system. So it doesn't look particularly like the robot is doesn't necessarily look humanoid, but it is animated. And the idea behind this robot is 3-axis motor. It has it can see, it can do facial recognition, it can do voice ID. It also can kind of have some of the configurations of Alexa. Some of you might know, has some AI capabilities, can learn about its interaction and help with a variety of tasks. Jibo is not a commercial robot anymore, not on the market, but the concept, I think, it was worth discovering. One of the things that I wanted to point out is that they did a study with children, adults, and older adults, and the blue areas suggest that the older adults were more open to using this robot consistently than the regular adults were and the children were. So I think this is important to note, that these types of social assistive robots and for use with elders, even elders with dementia and neuro issues, I think should and continue to be explored. I thought that this information about thinking about the Alexa, which is that AI unit that most people, like a lot of people have now, at least in America, in their homes, versus the Jibo. A study was done that showed that the Jibo was able to maintain elders' interest across the time, a 2-week period, for transactional type activity, entertainment, and social, and that the novelty of Alexa went down, the use of the Alexa went down, while the group that was using the Jibo was able to maintain interaction. The last system is this Paro robot, which most of you are already aware of. What I wanted to bring out is this idea that Paro is a soft robot, but it's made out of fur and has a variety of sensors that are within the system that is allowing it to sense light, to do auditory balance, tactile. This robot has probably been used the most for mental therapy, with patients with dementia. There's a lot of stuff out there on this robot. One of the things that I wanted to bring up on this is just an anecdote. A colleague of mine in Penn Nursing here is using the Paro in an inpatient setting. And when COVID occurred, there was a lot of pushback about using the Paro because of infection and disease. And there was a lot of desire for a robot companion that was completely wipeable, that could take bleach on it. And even though the manufacturer of Paro said that the Paro was, I'm blanking on the term, could withstand and was actually made for hospital environments, it took a lot of convincing to get this robot in that environment. So I think the use of soft materials and soft systems could be a solution. One, because if they're made to be easily wipeable, but still have that squishy, a companion-like feel, I think they could be really important in terms of supporting mental people with dementia, people with stroke, elders with isolation issues, things like that. I had just listed here some of Paro's abilities. If you're not familiar with Paro, I'm going to just quickly show this video. This is an old video that was published a while ago. And Paro was developed in Japan. So for the sake of time, I won't show the whole video, but one of the critical things about using these types of social robots, I think, is it's growing because of the rate of people the growing number of older people across the world. So this idea of using social and these companion type robots to support the elder, and Paro in particular have been shown to have distinctively quantifiable effects on mental health, depression, improving and reducing loneliness, and increasing communication across elders in a nursing home. And I think the next generation of these systems might need to then be capitalize more on novel materials of the social, the soft robotic new materials that are out there that could then deal with the issue that was brought up in COVID, in terms of if you're going to put these things in the hospital where infectious diseases are, how do we manage that and not spread the disease and still allow these systems to be used with a variety of people? I'm going to stop there and take questions. I know this was this kind of a big picture application kind of talk. If anyone have any questions, please feel free to ask them at this time.
Thank you, Michelle, for your presentation. I see Christian, please.
Yes, Michelle, can you hear me?
Yes, I can.
Thank you, Michelle, for your very nice presentation. I have a question about the role of the rehabilitation robot. In particular, what is, in your opinion, the best feature to build up, to develop a trustworthy social robot? So is the trust perceived by the users of the robot?
I didn't get the last part of the question. You said what would be the best feature to develop a what robot?
A trustworthy robot.
Oh, a trustworthy robot. Oh,
It's behavior or it's anthropomorphism or whatever.
It's a great question. I think it's maybe a little bit of both. I would say that the robot needs to be perceived as reliable and consistent. And then there also needs to be a matching between what the user is perceiving and what the robot's doing. Oftentimes, the robots, it's, for example, if the user is expecting that the robot's observing them and they do something funny and the robot doesn't react, then they're like, wait, is this robot really observing me or what's going on? If there's a mismatch between the behavior, the response, and the action of the user, then it lowers trust, right? If the robot makes errors and more and more errors, but we know this, like, then it also lowers trust. So if the robot is seen to be in like they're caring, oh, hi, Joe. If they see that the robot's making a connection and recognizing them, it increases trust. So there are lots of variables that I think modulate trust, and I think finding the one of the bigger ones is the mapping between the behavior and the action of the robot.
Okay, thank you so much, Michelle.
You're welcome.
I see Miranda with a raised hand.
Hello, hi, Michelle, can you hear me?
Yes, I can.
Okay, well, first of all, thank you for the presentation. I'm really interested in learning more about social robots, and I've obviously heard a little bit about Paro before, but that was really interesting to hear more about. One concern I've been wondering about, and I thought it might be really interesting to ask you about, is how can we take precautions to make sure that there isn't an ethical issue regarding vulnerable elderly people trusting too much in these socially assistive robots? For example, with the Paro, it does look like a toy, but it could also easily say, if someone has a vision impairment, be misconstrued as, say, a pet or something, and they become overly attached to the robot. So has there been any considerations regarding that, or is there any research you're looking into for that?
Yes, great question. There's actually a lot of work on this idea of ethical issues in terms of this level of like getting too attached or not getting too attached. If there's actually a lot of publication in terms of Paro and some people asking these questions in terms of the ethics of it. I think you have two groups. There are two kind of schools of thought. One is it's okay for some level of attachment if that allows the patient to increase their sense of not being alone, and then also increase their affect. They're no longer depressed. They're having and performing a connection in terms of communication. There's some schools of thought that says that's okay, and to a certain level, right? Because older people, especially someone with vision impairment, they're no longer able to take care of a real pet. So it may be okay then to allow them to bond with this robot. The other school of thought is that, like you're saying, there could be then a challenge when you're thinking it's not real. But I don't know. I'm in the first one, in the first school of thought that says, if it is not a danger to the elder, and the elder affect and appearance has been improved tremendously from having this robot as a companion, I think it is fine. However, there are lots of people writing about this issue, Miranda, and I would actually defer you to some folks who are more psychologists who talk a little bit about social ethics, about social robots. But I think there needs to just be a balance, right? And I think the caregiver and the clinician, in their use of the Paro, and when they bring it out into the circle of patients and how it seemed to increase communication, I think we can then rely on maybe the clinician and the caregiver to be the arbiter, right, of the use of the social robot, if there is a major concern about the ethics of it. I hope that answered the question.
Yeah, that's really good to hear. Thank you for providing that information. It's just something I was wondering, because if we push more towards soft robotic materials being used and soft robotic systems being used in social robots, then it could lead more towards, say, a deception almost. If we had humanoid robots that were made from soft materials that could possibly in the long run look more human-esque, then there could be an issue there. But you did make some very good points, and I'll definitely have a look at the psychology side of things. Thank you again.
You're welcome.
Okay, we have time for one last question. So I invite the other student to contact Michelle by email. Please, Kathleen.
Hi, Michelle.
Hi.
Thank you so much for the discussion. I thought it was really interesting, especially the parts where you talk about how things changed during COVID. I thought that was very, very interesting. I was just wondering, I know that there's been some work done into the uncanny valley aspect of social robots, how you don't want them to look creepy. And you talked a little bit about the level of animation that you should have for the faces of the robot. But, as people that develop soft manipulators and soft grippers, I was wondering if you had any thoughts about what manipulators and grippers should look like, if it would be creepy for elderly if they looked too much like human hands, if they should look cartoonish. I was just wondering your thoughts on that.
Wow, that's a good question. Maybe Loredana would be the better person to answer this, because it's funny. I don't remember or recall seeing anyone doing a research on kind of if the hand of the social robot looks more like a regular hand, are people kind of being creeped out at that. Usually it's the entire form. When they do the uncanny valley studies, it's the entire form of the robot that people are absorbing, and they're usually not like focused just on the hand. You know, they're and majority of it, it's like, how does the entire thing look, or how, especially the face, right? I don't know, Caitlin, this might be a study that you might need to perform. Because I really, I can't say I know the answer to whether they would be creeped out or not. My instinct says maybe no, because when we did this focus group with the elders and asking them about their desire for a humanoid versus a like a robot that doesn't look very humanoid, the things that they brought up didn't have anything to do with kind of the manipulation part. A lot of it was perceived control, and that the robot is for example, they talked about the voice, how the robot spoke to them. They talked about how the robot, for example, we showed them images of robots that had a humanoid face or ones that were like reflected eyes. And the humanoid face, they were like, that could be good, but that could be creepy. So the things they were focusing on were not necessarily how it was doing the manipulation. There was a sense of, it needs to be safe. It needs to be able to give me the object that it's passing and in a safe way. But it didn't really, there wasn't like a focus on, is the hand anthropomorphic hand or not. So my guess would be the hand may play less of a role, and the dexterity of the hand and the safety in transitioning objects might play a larger role.
Sure. Thank you so much for that.
You're welcome.
Okay, thank you, Michelle, for your talk. We can move ahead with the next speaker, Professor Connor Walsh. Let me introduce him. Professor Connor Walsh is the Paul Almeida Professor of Engineering and Applied Science at the John Paulson Harvard School of Engineering and Applied Sciences, and an associate faculty member at the Wyss Institute for Biological Inspired Engineering. He is the founder of the Harvard Biodesign Lab, which brings together researchers from the engineering, industrial design, apparel, clinical, and business communities to develop new disruptive robotic technologies for augmenting and restoring human performance. This research includes new approaches